Welcome back. Today we're going to talk about curve sketching. Last time we discussed the use of first and second derivative in increasing and decreasing intervals and concavity of a graph. Today we're going to put all the information that we've learned so far into one section and discuss that in terms of graphing, the use of those information to graphing of a function. So to graph a function, normally we will try to figure out these specific information. First, you need to figure out what is the domain of the function. Then you find out the intercepts. Intercept means when the function crosses the x-axis or the y-axis. So x-intercept and y-intercept. Symmetry. We've discussed symmetry about the origin as well as symmetry about the y-axis. So there would be an odd or even function. Sometimes the functions are odd or even. There are cases that it's neither, so there is no symmetry. And we have some type of functions like trigonometric functions that have periodic behavior. So if you find the period of the function, then you don't need to graph the function over the whole domain. You can just graph it over a specific interval, then repeat the same graph. After that, we will find asymptotes. We had vertical and horizontal asymptotes. And in step 5 would be find the increasing and decreasing interval through the first derivative, which corresponds to local maximum and minimum points. We can find those as well. And finally, using the second derivative, we can find the concavity and inflection points. By finding these information, we have enough detail about the graph that we can sketch the graph of the function. And I've wrote down a couple of examples, and what I did is I wrote the function as well as the derivatives, but try to start with the function without having the derivative. So start with f of x and go through the quotient rule and figure out first derivative, because you need to find the first derivative for the increasing and decreasing interval. Then take another derivative from that through the quotient again and find the second derivative. I didn't want to go through the process of doing this over and over, so this way I just found the derivatives already and wrote it. But normally they only give you the function, they do not give you the derivatives. So make sure that you know how to find the derivatives. It's just the quotient rule, and simplification is a part of it. So what we do is we only look at the function f at the moment, and we need to figure out the domain of the function. So step 1 is to find the domain. So what is the domain of f? You have to figure out where the denominator is 0. So to find the domain, you write domain. We find out where the denominator is 0 and exclude those points. So a fraction cannot have a 0 in the denominator, therefore x squared minus 4 equal to 0 cannot be 0 in reality, so we want to figure out where this denominator is 0. You can move the 4 to the other side and take a square root. X would be plus or minus 2. So what we can exclude and say domain is all real numbers except 2 and negative 2. All real numbers except 2 and negative 2. You can write this interval negative infinity to negative 2, negative 2 to positive 2, and 2 to positive infinity. Either way is fine. Okay, step 2 would be to find the intercepts. So first, let's figure out the x-intercept. What is the x-intercept? You have to find the coordinate. Okay, maybe there are more than one x-intercept or more than 2 x-intercepts. So how do we find the x-intercept? Is say the function must be 0. If you forget this, just let me remind you. You have a curve. It crosses the x-axis at certain points. You need to figure out these points. What do you know about the graph is about the function at those points is that the y value is 0. That means the function is 0. So I'll set the function equal to 0. I'll say 3x squared divided by x squared minus 4 equals to 0. When does this fraction equals to 0? Is if the numerator is 0. So 3x squared must be 0. And the solution to that is divide by 3, take a square root, x must be 0. So x is 0. And since it's a x-intercept point, y value is 0. You can replace 0 back in, but there is no need actually. How about the y-intercept? Y-intercept, x is given 0. You need to figure out y-intercept means where does this function crosses the y-axis. That means the x is given 0, So you figure out what is the y value. Replace 0 into the function f. F of 0 is simply 3 times 0 squared divided by 0 squared minus 4, which becomes 0 again. So you have the x and y intercept, which are basically the same thing. In this case, it's the origin. So that means the function only crosses at the origin. It doesn't cross anywhere else. It doesn't cross the x-axis at any other point. So the only time that you would see the function is either it would be something like this, or maybe something like that, or the other way. One of these cases. Okay, so you don't have such a graph. You cannot cross the x-axis anywhere else. Otherwise, you would have an x-intercept. Okay, let's talk about the symmetry. Third step is to find the symmetry. The symmetry would be, you just need to figure out what is f of negative x first. To find the symmetry, if it's an even or odd function, you find f of negative x. This was from first chapter. 3 times negative x squared divided by negative x squared minus 4. Every time you see x, you replace negative x for it. If you simplify it, it would be 3x squared divided by x squared minus 4. Okay, now compare the function that you found, f of negative x, which is 3x squared minus 4. Right, 3x squared divided by x squared minus 4. This is f of negative x. Compare this with the original function. What do you see? You see that the two functions are equal. If that happens, if f of x equals to f of negative x, that means the function was an even function. This is an even function, which means you have symmetry about y-axis. That means whenever you graph the function, if you graph the right-hand side, however it looks like, exactly you would have the same shape on the left-hand side. Doesn't really matter. You should have this symmetry. Okay, so far we know that there is a symmetry about the y-axis, so we kind of need only to graph one side of the function. The left side would be very symmetric. And we also know that the x and y intercept happens to be at this origin only. So the graph would somehow look like something like this, maybe. Symmetric. Okay, these are just explaining what does this information give you. Step 4, asymptotes. So how do you find the asymptotes? Is these excluded points from the domain are always the points that you have to look to find vertical asymptote. So if you're looking for vertical asymptote, let me mention this very carefully. If you're looking for vertical asymptote, normally you look at the excluded points in the domain. You look at x equal to 2 and x equal to negative 2. They may be vertical asymptotes or may not be. These are candidates. So these, every time you see this excluded point, it doesn't mean that you would have vertical asymptotes there. Okay, it means if you're finding the vertical asymptotes, look at these 2 points to see how does the function behave around x equal to 2 and how does it behave around x equal to negative 2. That means calculate the limit of the function as x approaches to 2. Maybe from one side is good enough. And the same for x equal to negative 2. From right or left doesn't really matter. That means pick a point close to 2, replace it in the function to see what happens. If you replace something close to 2, if you replace 2, you will get, if you replace 2 into the function, what you get is 3 times 2 squared divided by 2 squared minus 4. And what you get is 12 over 0, which you should say, this is undefined. But since you're discussing it in the limit sense, this doesn't really mean replace 2. It means something close to 2. So close to 2 means 2.01, for example. Replace 2.01 into the, for x, figure out what happens. If you do that, what you get is, you'll get 12, let's say 0.03. I'm not sure this is correct, but I'm just estimating, guessing what happens. Let's say this is what you get in the numerator. The denominator is 0.002 or something. Almost. This is not equal. This is almost something like this. And when you calculate this, this would be something like 1200. It may be 1400, whatever. So what does it tell you? This says the closer you get to 2, the bigger this y value gets, because this is representing the y value of the function, right? So the y value is basically approaching to infinity. So if that happens, you're saying x approaches to 2, y goes toward infinity. If that happens, means you're getting close to 2, the y value is increasing. Therefore, 2 must be a vertical asymptote. That was the idea of the vertical asymptote. So in this case, x equal to 2 is a vertical asymptote. Similarly, if you check -2, from left side, you will see that you will have, again, positive infinity as the limit. So in this case, x post +2 and -2 are vertical asymptote. A good hint to see if you have vertical asymptote is replace the number in limit sense. Replace the number into the function. If you get a constant like 12 divided by 0, if this happens, that's a vertical asymptote. If you get 0 over 0, that means you can simplify the function. So first simplify the function, then try again. Continue this process until either you get a number or you get a constant like 2 divided by 0 or 20 divided by 0. The only time that you can say for sure there is a vertical asymptote is if after simplifying you have a constant divided by 0. If this happens, then that point that you picked, in this case, x equal to -2 is a vertical asymptote. Because at least in one side, the function will approach to infinity. It could be positive or negative infinity, we don't really care. So it's vertical asymptote, this is how you focus on vertical asymptote. And horizontal asymptote, last time we talked about this, you calculate the limit. Let's calculate this limit. Limit of the function, which is x squared, 3x squared divided by x squared minus 4 as x approaches to both infinity and then you try x approaches negative infinity. Consider both cases. If you approach to positive infinity, what you would get is 3x squared divided by the biggest term from last time. You should remember this. Divide everything by the largest term in the denominator and numerator. So what you get is limit, numerator is 3 divided by 1 minus 4 over x squared. Sorry, I wrote it too close to each other. I wanted to keep have some space for later. As x approaches to infinity, this term always approaches to 0. It doesn't really matter if it's positive infinity or negative infinity. So this is gone. So what you have is the limit is 3 divided by 1, which is simply 3. So the horizontal asymptote happens at y equals to 3. This is important to know the horizontal asymptote and the vertical asymptote. So what does it mean? It means if you're graphing the function, at 2, you have vertical asymptote. -2, there is another vertical asymptote. At 3, you have a horizontal asymptote. So the graph would kind of look like maybe something like this, or this is one choice, or something like that. It has to approach both asymptotes. Or maybe on this side it will look like something like this, approaching the asymptotes. These are all expected from the vertical and the horizontal asymptote. Sorry about that. So now that we figure out the vertical and horizontal asymptote, we can look at the increasing and decreasing interval and concavity of and inflection point. So we already have the derivative. The derivatives are given. So I'm going to use, this is the first derivative, -24 divided by, I think it's supposed to be -24x. I'm not sure. Let me check this. -24. I think I'm expecting -24x. let's calculate the first derivative just to make sure that is correct. So f of x was given, what was f of x? F of x was 3x squared divided by x squared minus 4. And so the first derivative would be derivative of the numerator is 6x times the denominator x squared minus 4 minus the derivative of the denominator, which is 2x times the numerator 3x squared, and subtract that from each other, then divide by denominator squared, x squared minus 4 squared. The only thing that you need to do is just simplify. Distribute this and subtract it from the other one. 6x times x squared is 6x cubed, and here you have another 6x cubed, so these two will cancel out. And negative 6 times, yeah, so there should be an x here. Negative 24x over x squared minus. There you go. Okay, make sure you calculate the derivatives correctly. Don't make the same mistakes that I do. Okay, so let me erase this. Okay, so now that we have the first derivative, 5, which is negative 24x divided by x squared minus 4 squared. We need to figure out the critical numbers and then the increasing and decreasing interval and correspond to that local maximum. To find that, first we find the critical numbers. Critical number is where the derivative is 0 or undefined. So the derivative is 0 when the numerator is 0. So that happens at x equal to 0. These are critical numbers. Critical numbers. And the derivative is undefined where the denominator is 0. Denominator is 0 is x equal to 2 and x equal to negative 2. 2 and negative 2 do not belong to the domain. So in reality, these are not the points that could be local maximum minimum. But in the critical number, you should still consider them for a moment. You cannot say these are critical numbers because they do not belong to the domain. But I'm going to keep them just because I want to draw the number line for the first derivative. Sorry. Okay, so here, let's draw the number line. First derivative, I'm going to pick the critical number, 0. At 0, here's what is important. At 0, the derivative is 0. But at the other 2 points, at 2 and negative 2, negative 2 and 2, these are points where the derivative does not exist. But 2 and negative 2 do not belong to the domain. So maybe I should say undefined at these points, or do not belong to the domain. It would be correct, better. Or you can say does not exist, either way, D and E. Just make sure that you notice that these points, in this case, they do not belong to the domain, so they cannot be local maximum and minimum. Do not make that mistake. Okay, so what we do is we look at the increasing and decreasing interval by picking test points. So I'll pick something like negative 3, negative 1, 1, and 3. I'll replace these into the first derivative. I replace it into the first derivative. If you replace negative 3, what you get is negative 24 times negative 3. That would be a positive number. Denominator is squared. The denominator is always positive. So positive divided by positive, you'll get a positive value. If you replace negative 1, you'll still get a positive number. If you replace 1, you will get negative. And if you replace 3, you'll still get negative. So now you see there is no alternating behavior. So the function is increasing, then again increasing. Here is decreasing and decreasing. This is for the first derivative, so I know the increasing and decreasing. What can we say about local maximum and minimum? These 2 points, again, they are not local max and min. There does not exist points, these 2 and negative 2. They do not belong to the domain, so you cannot discuss the local maximum and minimum at those points at all. But here at 0, if you look at 0, you have an increasing, then turns into a decreasing. So it means this is a local maximum point. I have 0 as a local maximum. If you want a y value, you replace 0 into the original function, find out what is f of 0, that gives you the y value. But we already have f of 0, which is 0. That was the origin, which was a part of the graph. It was the x-intercept. It's good to find the corresponding y value as well. So here, we found step 5. Step 6 would be to look at the second derivative and find the critical number for the second derivative. So let's look at the second derivative. Second derivative is 24 times 3x squared plus 4. So 24 times 3x squared plus 4. And the denominator is x squared minus 4 cubed. There is simplest. This is a simplified version of the derivative. Normally, if you want to find the inflection points and critical numbers, it's better to simplify the function. Okay, again. Now find the critical number for the second derivative. So when does the second derivative equal to 0? Critical numbers, I want to say for the second derivative, just to make sure that it's not the critical number for the first. So again, numerator or the denominator equal to 0 would give you critical numbers. The numerator would be 0 if 3x squared plus 4 is 0. That constant outside doesn't make any difference. You can divide both sides. If there was a 24 here, you can divide 24 on both sides. That's why I didn't write it. And if you solve this, what you get is x equals plus or minus square root of -4/3, which is a imaginary number because you have a square root of a negative number. So this is not an acceptable solution. So this means there is no solution to that. But if you set the denominator equal to 0, then what we get is again x equal to 2 and -2. Again, these 2 points do not belong to the domain. So they cannot count as critical numbers, but on the number line you still show them because they cut down the number line into multiple pieces. So here, this is second derivative at 2 and -2. And what do we know? This point, second derivative did not exist. Does not exist doesn't mean that it's not a part of the domain. I just wanted to make sure that you do not consider them as inflection point because there is no other point as a critical number. So there is no inflection point. How about test points? You pick -3, 0, and 3. Replace into the second derivative. You replace -3. Numerator would be positive. Denominator would be positive number. So here you will have a positive. If you replace 0, what you would get is positive divided by negative. So you'll get negative, and here you get positive. Again, you don't need to figure out what is the number precisely. You're just looking for the sign. So what does this plus sign mean? For the second derivative, it means concavity. So this is concave up. Here you would have a concave down curve, and again, concave up. The test points do not matter. I'm going to erase the test point so you do not mix it up. Okay. Now, given all these information, can we put it together and draw the function? So what I'm going to do is I'm going to try to erase some of these. We can draw the function in the corner next to all this data. Okay. Maybe I could have made this a bit smaller. Okay. Yeah, we still have access. So here, let me draw a table. You can draw a table and look at the data from these two in the table as well. Okay, so the important points, this is for the function, first derivative, second derivative. The important points, happen to be at -2, 0, and 2, because these are correspond to either vertical asymptotes or a critical number or inflection point. In this case, there is no inflection point. Okay. At -2, what did we figure out is -2, you have vertical asymptote at 2 and both 2 and -2. So at 2 and -2, I'm going to say vertical asymptote. Vertical asymptote. 0 is a x-intercept, and the y value correspond to that was 0. For this first derivative, we found that 0 is a local max. I can say local max. And if there was an inflection point, I would have mentioned it in this second derivative, but there is no inflection point, so I'm not going to write anything. So now, information from the first derivative is that the function is increasing here, decreasing, and decreasing. Information from the second number line is that the function is concave up. Here, it's important, between -2 to 2, look at this part of the curve, function is concave down. So here is concave down, here is still concave down, between -2 and 2. And 0 is still concave down as well, but I'm just trying to trying to discuss it in each section. At 2 to positive infinity, the function concave up. 2 to positive infinity is concave up. Now correspond to each section. If you have an increasing function and concave upward, how does it look like? Increasing function concave up is something like this. It should be increasing and concave up. If you add this portion to it, this side is not concave up. Sorry, it's not increasing. So that's not possible. So the curve has to be going increasing and concave up. And the next section would be increasing concave down. So this, again, increasing, and then decreasing concave down, decreasing concave down, and decreasing concave up, something like that. So I expect the graph to have these 4 pieces connected to each other. Or since there is vertical asymptote, it kind of behaves around the vertical asymptote in that shape. So let's draw this curve precisely. You can pick a couple of more points if you want, but good enough. Okay, so we learned that x equals to 3 is a horizontal asymptote. I'm going to draw a horizontal asymptote. X equals to 3. We learned that -2 and 2 are vertical asymptotes. -2 and 2, vertical asymptote. You don't need to be super precise in the homework. The good thing is that they give you the graph, but it's not always an option to have the graph. Sometimes they give you this data and tell you to graph the function. So here, what we can do is we can focus that 0 and 0 is a local maximum, and that's the only x-intercept. So the function only crosses at this point. And now I look at the curves. Look at the first part of the curve. It should be increasing and concave up. And you have to approach the horizontal asymptote as well on both sides. So you have to either approach to this horizontal like that or like this on both sides. One of these two. Okay, based on the first information that we have is toward -infinity to -2. So from -infinity to -2, I should have this type of graph, the increasing concave up. The only choice that I have is okay, so that's the first part of the graph, up to -2. Then from -2 to 0, you should have a increasing function and concave down. Again, you have to approach to this horizontal asymptote. If you start from here, it's not going to be increasing. You do not have the option to go up anymore because it's not the case. So you start from here, here increasing, and you have to approach to that origin. because you need to reach the origin. That's the only time that you cross the x-axis. And then from 0 to 2, decreasing concave down, decreasing concave down, approaching horizontal asymptote, vertical asymptote. And then finally, in the last, on the right side, since we knew the graph is symmetric, basically you don't need to look at the curve anymore. You can just, based on symmetry, you don't need to look at the data. Based on symmetry, you can graph this. So this is how the function looks like. This is the graph of f of x, which equals to 3x squared divided by x squared minus 1. And we used all the information. What is the domain? Domain is all the numbers except 2 and negative 2. You see that 2 and negative 2, there is no y value since they are vertical asymptote. You have horizontal asymptote, you have x and y intercepts, we have symmetry, we used local increasing and decreasing, we have only one local maximum, which is at 0, there's no local minimum. All these information together and we get this graph. Okay, this is a good example to see if you're dealing with rational functions, has all the information involved. You can look at another example. Again, the derivatives, I've calculated these derivatives. You can calculate it through quotient rule and chain rule in case if it's necessary. And try to simplify it. So let's graph this function as well. What is the first step? First step is to find the domain. Okay. Domain would be all real numbers except the points that makes the denominator 0. Where do you get 1 plus cosine x equal to 0? Which means, where do you have cosine to be negative 1? And that happens when x equals to pi. That's the only time that cosine is negative 1. But in reality, that's not the only time. This is the only time from 0 to 2 pi. After that, at 3 pi, 5 pi, 7 pi. Every 2 pi, you will get this point. So instead of writing all these, I will say pi and plus all the multiples of that, all the rotations, 2n pi. This is for any n. So I said the domain is all real numbers except these points, pi plus 2n pi. Okay. The good thing about this function is that it has the periodic behavior. So after pi, every 2 pi, you'll see the same graph over and over. So this was the first step, find the domain. Second step was to find x and y intercept. Here was the second step. I don't need to go up anymore. So second step would be to find the intersects x and y intercept. So y intercept, replace x with 0. Sine of 0 is 0, so you'll get 0. And x intercept, when do you get the function to be 0? That means where do you get the y to be 0? Means set the function equal to 0, sine x divided by 1 plus cosine x equal to 0. This is 0 if the numerator is only 0, so I don't really care about the denominator. Sine is 0 at x equal to 0 and pi, and 2 pi, and so on. But look at the points that are not in the domain. At pi, it's not possible to have an x value because it's not in the domain. And to have a y value, pi is not acceptable. Therefore, 3 pi would not be acceptable. The only points that we have 0 is at 0, 2 pi, and any other multiple. So again, similarly, x equal to 0, 2 pi, and so on. So I'll say it is at 0 plus 2n pi, and their corresponding y value is 0. This is a shorter way of writing it. Then after we find the domain and y-intercept, you can look at the symmetry, but in this case, I'm going to discuss the periodic behavior. Periodic function in this case, which means sine and cosine by itself, each one, simple sine and cosine, they have period of 2 pi. Every 2 pi, you will get the same function. So any combination of these guys, if there is no coefficient inside, if there is no 2 in here, then the period would still be 2 pi. So here is period of function is 2 pi. I should say period is 2 pi. That means You just need to graph the function over the interval 0 to 2 pi. That would be good enough. If you graph this, if you graph the function over this interval, then you just repeat the same curve over and over. So we focus only on this interval at this moment on. We don't really care about anything else. So I can look at the x-intercept and say only 0 and 0. And maybe 2 pi and 2 pi and 0 as well, the endpoints. Okay. Next step would be to find the vertical and horizontal asymptote. So vertical asymptote, look at the critical number. What is the critical number? The critical number was at where the derivative is, where the denominator is 0. The choice for the vertical asymptote. So in this case, where do we get the denominator to be 0? It happens to be at x equal to pi. So vertical asymptote, is it x equal to pi? That's the question that we want to figure out. What you need to calculate is limit x approaches to pi, the function sine x divided by 1 plus cosine x. And we've talked about this. If it was, if you replace pi into the function, what you get is sine 0 divided by 1 plus sine pi divided by 1 plus cosine pi. And what does it give you is sine of pi is 0, cosine of pi is -1, so you'll get 0 over 0. So now the question is this acceptable to be a vertical asymptote or not? Not really, because this means you can simplify this function, sine x over 1 plus cosine x. So what I'm going to do is, instead of doing this, I'm going to simplify the function first. I'm going to multiply 1 minus cosine x to simplify, 1 minus cosine x. You may ask me, why do I do this? I'm going to show you the trick. If you multiply a conjugate, what you get is 1 distribute this denominator. You will get 1 minus cosine plus cosine, again minus cosine squared. So you get 1 minus cosine squared x. Numerator is sine times 1 minus cosine x. Sine x times 1 minus cosine x. Sorry, I'm writing it too messy. Sine x 1 minus cosine x. Okay, the identity for 1 minus cosine squared x is sine squared x. The Pythagorean identity, sine x 1 minus cosine x divided by sine squared x, and all divided by x approaches to. So now, can I simplify it? You can cancel out one of the signs. This whole purpose was to get rid of one of these, either the numerator or the denominator. We wanted to cancel out the sign. So what we got is limit 1 minus cosine x divided by sine x as x approaches to pi. Now, if you replace pi into the function, what you get is 1 minus cosine pi would be 2, and sine pi is 0. Now, since you have a constant divided by 0, you can say, yes, x equal to pi is a vertical asymptote. So all this work was to get to this point that you have a constant divided by 0. This is undefined in terms of value, but in terms of limit, this might approach to either positive or negative infinity. Okay, so we have a vertical asymptote. Again, every 2 pi you will have the same vertical asymptote. Horizontal asymptote, let x approach to infinity. What do you get is sine infinity divided by 1 plus cosine infinity, which in this case is not possible. You would not have any limit. So there is no horizontal asymptote, because sine infinity is not a constant value. Sine is just alternating, as well as cosine is alternating. So if you calculate the limit infinities, you would not get a number. And that's what you expect, because you have a periodic function. So it doesn't approach to any constant value. It's just periodically changes. So no horizontal asymptote. And then we can look at the derivatives. Find the critical numbers. So first derivative, which is, in this case, it's kind of simple. I'm going to write a bit smaller. Okay, so first derivative, f prime is 1 f prime x equals 1 divided by 1 plus cosine x. And we're going to figure out where this derivative equals to 0. So here, numerator equal to 0. This is to find the critical number, which is not possible. So denominator equal to 0, 1 plus cosine x equal to 0. And that is when x equals to pi again. We've solved this already. And this is not acceptable as a critical number again. Not acceptable as a critical number. But we still consider it on the number line. So I'm gonna make sure that you be careful at this point. When you draw the number line, since we already stopped at 0 to 2 pi, I'm not gonna go beyond 2 pi. I say this is 2 pi, here's 0. I'll only pick the test points in this interval, because after that the function behaves periodically. So this is for the first derivative. I'll pick a test point, something like pi half, not negative. Pi half, and I'll pick 3 pi half. Replace it in the first derivative. What you get is a positive number. You replace 3 pi half, you'll still get a positive number. What does it tell you? It tells you that the function is increasing and always increasing. So there is no local maximum or local minimum because there is no alternating sign. And at the point pi, there was no derivative. Neither this point belongs to the domain since it's a vertical asymptote. Okay, if we look at the second derivative, second derivative is given as sine x divided by 1 plus cosine x squared. So sine x divided by 1 plus cosine x squared. Again, to find the critical number of the second derivative, set the numerator equal to 0, as well as set the denominator equal to 0. The solutions are x equal to 0, pi, 2 pi, and so on. And here the solution is x equal to pi. Again, pi does not exist, but you have to show it on the number line. Second derivative. 2 pi, 0. I cannot go beyond these. Pi. Okay, so what is the test point? I'll pick pi half. I'll pick 3 pi half again. Replacing the first derivative in the second derivative, replacing pi half will give you sine pi half, which is 1. Divided by denominator is always positive, so you'll get a positive number. If you replace 3 pi half, you'll get a negative number. So it means you have a concave up to a concave down curve. You might ask if pi is an inflection point, and the answer is no, this is not an inflection point. Not an inflection point. Why not? Because it's not in the domain, so this is not possible. But if you would have extended this number line and say, since the domain is all real numbers except only this specific point pi, because this will continue, you will have the same graph over and over. You will get this shape. So then 0 would be an inflection point, 2 pi would be an inflection point. So I'll say 0, this is an inflection point. You'll see it when you graph the function, but it's good to know at this point as well. So I will consider 0, 2 pi, this is an inflection point. Because if you continue to graph this over and over, you will have alternating sign, plus, minus, where the derivative basically exists and you can talk about it. At pi, you have an alternating sign, but the derivative did not exist. Okay, so let's put all these into one table again. I'm going to consider only an interval 0 to 2 pi. I'm not going to go beyond that. You could have picked negative pi to pi, negative 2 pi to 2 pi, but it's too much. I'll only pick this interval, then I'll regraph it. Function. First derivative. And second derivative. If I fill in all this data, then I should have a sketch of the graph. Maybe sketch. Okay. Pi was a vertical asymptote. It was a vertical asymptote. 0 and 2 pi turn out to be inflection point. So I can say here inflection point for 0 and 2 pi. Even if you don't find it at this moment, you will see it when you graph it. Okay. Was there x and y intercept? We had x intercept at 0 and at 2 pi and so on. So found the x intercepts to happen at these points. The y intercept was 0 and 0 as well. Horizontal asymptote, there was no horizontal asymptote, neither you can use this graph to show it, but here it was increasing, always. First derivative, increasing and increasing. Then concavity was concave up and concave down. So concave up, increasing concave up will look like this. Increasing concave down will look like that. So you just need to repeat these type of curves on the left side and on the right side. You will get the same shape over and over. Okay. Let's draw these in one graph. Okay, so how does it look like? You will find 0, 0. This is one of the point. And I'll find 2 pi maybe here. And this. And call this pi. At pi, we have vertical asymptote. That means if I look at negative pi and to negative 2 pi here, at negative pi I should have vertical asymptote as well. Every 2 pi you will see the same behavior. So every distance of 2 pi, this is 2 pi, you will get the same vertical asymptote. So another at 3 pi you will have a vertical asymptote again. That's why I didn't graph the function. I didn't get the domain to be all, didn't pick over all real numbers. I only focused on 0 to 2 pi. So now we have the x-intercept at 0 as well as at 2 pi, and you have vertical asymptote at pi. So the graph has to reach to these 2 points and approaches to vertical asymptote. And based on the shape, from 0, it should be increasing and concave up toward the vertical asymptote. And on the other side, it should be from the vertical asymptote, increasing concave down. You'll expect, if I could have drawn this better, the concavity is kind of was important. Okay, now if you draw this over and over, what you see is here, the same curve. Just regraphing it. You look at this. You look at this section of the graph. It's from 0 to negative 2 pi to 0. Compare it with this section. It should be exactly the same graph. And if you continue, maybe I should pick a different color. If you continue here, this color, and the next graph would be something like this. You'll get the same curve over and over. And so now you would see that there is an inflection point at 0, 2 pi. These are inflection points. It wasn't clear on the number line, but you will see that there is change of concavity at this point, as well as at 2 pi, as well as at 4 pi, all these points. This was another inflection point. Okay, I'm gonna stop at this moment, but this is not the end of this section. We have to talk about slant asymptote, and we do example of that as well. But now, just to make sure this video is not too long, I'm gonna stop at this point.